Hello everyone, in today's class we're going to look at how pressure varies when acting on a element of fluid. So we'll start off with a small element of fluid in the shape of a right angle triangle that has a coordination of x, y, and z, y, and x. Okay. We'll assume this to be changing z from here, from this point to that point, that's changing z, and from this point to that point, that'll be changing y, and this here we'll call changing s. Oops. Okay, now there is a force acting from the left. We'll call that Py because it's acting on the y direction, y axis. There's a pressure force acting from the bottom going up. We'll call that Pz. And there's a pressure force acting in an angle. We'll call that P. Okay. Now what we want to do is we want to find the value of P, Py, and Pz. Okay. The right angle triangle has a angle of theta, which is the same angle here. If we get the component forces for that magnitude, we'll end up with the same angle here, theta. Now we'll call this to be Py prime because it's acting in the y direction, but the opposite side, it's going from left to right, so it'll be minus, whereas this one is going from left to right. This will be positive, and this is from right to left, so it'll be negative. Anyway, we'll call that Py prime, and we'll call this here Pz prime, the pressure force acting in the z direction, prime. Okay? Now the prime is just to distinguish it from Pz and Py. That's the only reason I'm using prime. Now, Py prime, if we look at this angle here, the sine of this angle equals to the opposite over the hypotenuse. So sine theta equals the opposite, which is Py prime over the hypotenuse P. Therefore, Py prime equals P sine theta. Okay? Now, let's go ahead and solve for the sum of forces in the y direction. The sum of forces in the y direction, we'll start off with this. So now, since we're using pressures instead of forces, we need to keep into consideration that pressure equals force over area. Therefore, force equals pressure times area. So when we are performing a sum of forces, we need to take the pressure times the area it's acting perpendicular on. Now the area, it's for Py, the area is a change in z times x. The unit x, we're going to assume it to be 1 unit out to the board. So this triangle looks like this. When the x direction is included, it'll look like this. Let me fix that. So this here is the 1 unit x we're assuming. Okay? Now, so let's go back to finding the sum of forces in the y direction. We'll start off with Py. So it's Py times the area it's acting on, which is change in z times 1 unit x, so it'll be py times the area, which is change in z, times 1 minus this force here. It's the component force here, which is going right to left, therefore it'll be negative. It's called py prime, which we found to be minus p sine theta times the area, which is change in s times 1 unit x coming out of the board. So times change in s times 1 equals to 0. There's no y pressure force is acting here, so that will be 0. So the next step is we're going to change delta z in terms of delta s. How can we go about that? Well, if we look at this triangle here, if we want to find sine theta will equal to change in z over the hypotenuse, which is change in s. So sine theta equals change in z over change in s. Therefore, change in z equals to change in s times sine theta. We can go ahead and substitute that into change in z. Therefore, we'll have py change in s sine theta times 1 minus p sine theta times change in s times 1 equals 0. Now we can cancel the like terms, which is sine theta change in s 1 1. We'll be left with py equals p. The same thing will be true if we found the sum of forces in the z direction. We'll get that p equals pz. The point is that the pressure equals py equals pz, which is Pascal's law, which basically means that if there is a small element of fluid, the forces acting on that fluid from any direction and any angle are all the same, as long as it's a small element of fluid. Yes, we already knew that, but this is the proof for it, and that this process here is how we got to this conclusion and that proof. Now, let's look at another element of fluid. This time we'll look at it differently. We'll say that this is a small element of fluid with the weight pulling down and pressure in the middle. Now there's forces acting on the element of fluid from all directions. There's one acting from the left, one acting from the right, one acting from the top, one acting from the bottom. And the reason all the arrows is facing the element of fluid is because it's being compressed. The pressure forces are compressing that element of fluid. We have the same coordination as before, which is z, x, y, and z. Okay, this will be our change in z. This will be our change in y. Actually, this we'll take it in terms of differentials. This will be our dz. This will be our dy. Okay. Now the force acting from the left side is P, pressure, minus dp dy is here, dy over 2 dz. Okay? And the pressure acting from the right to the element of fluid is P plus this dP dy over 2 dz. The pressure acting from the bottom is P minus, okay, dP dz divided by 2 times dy. And the pressure acting from the top, which is P plus dP dz over 2 dy. Okay? Now, if we solve for the sum of pressure forces, the sum of forces in the y direction, we'll get P minus dP dy over 2 dz minus P plus dP dy over 2 dz equals 0. Okay, this will cancel. We'll be left with negative dP dy dz equals 0. If we move this to the other side, over here, we'll end up with dP over dy equals 0. The same thing will apply in the x direction. dP over dx equals 0, which basically means that the pressure does not change in the x or y direction, meaning that the pressure does not change in horizontal planes. Pressure does not change in horizontal planes. So if you have a swimming pool looking like this, the pressure at any point in this plane, this, if we say this is our axis, this is our coordination, z, x, y, anywhere in the xy plane, the pressure will be the same. We'll find out later that it will only change as the vertical z direction changes, the pressure will change. But anyway, so far we proved that the pressure does not change in a horizontal plane. So the pressure anywhere in this plane here is the same. Same thing here in this plane. The pressure anywhere in this plane is the same, but the pressure here and the pressure here are totally different. We'll find that out later. So let's keep going. If we solve for the sum of forces in the z direction, the vertical direction, okay, we'll get P minus dP dz over 2 dy, so I'm taking this and this, okay, minus P plus, which is the force acting from above, dP dz over 2 dy minus the weight will equal to 0. Let me fix this. Equals 0. Okay. The weight is gamma, specific weight, dy dz times 1 unit x coming out of the board. Therefore, this and that will cancel. This and that will cancel. Okay. These two will add up to 1. Will cancel as dz. Okay. We'll be left with dP dz, change in pressure over change in vertical direction over change in z, minus gamma equals 0. Therefore, dP over dz equals negative gamma, meaning that change in pressure equals change in the vertical axis times the specific weight, meaning that pressure increases in downward direction. Again, coming to our body of water or swimming pool. As we said before, the pressure at any horizontal plane is the same, but the pressure at this plane and this plane is different. Why? Because there was a change in elevation, there was a change in vertical in the z direction. Therefore, pressure changes in the vertical direction and it does not change in the horizontal direction. That's the second proof. See you on the next class where we're going to do a couple of examples. See you then.